Welcome back. We're going to look at a few additional examples of these work and force problems in physics, and what is the work required to remove a liquid from a tank. So let's just jump right in. Alright, suppose that I have a tank, a cylindrical tank. Suppose that my surface, so this tank is buried under the ground. So the surface is buried 3 meters, or the tank is buried 3 meters under the surface. Right, the radius of this tank is 2 meters, and the height of the tank is 4 meters. It's filled with a liquid. And the density of that liquid is equal to 1,500 kilograms per cubic meter. My question is, what is the work required to pump this liquid to the surface? Okay, that's what we want. Work to pump to the surface. Alright, so let's just remind ourselves of the big ideas here. Work is force times distance. So let's build this. I'm going to reproduce my picture a little bit smaller over on the left. So I have some space to work. Right, so I have 3 meters, I have 2 meters, and I have 4 meters. Okay, so remember our whole idea here. The whole idea for all of these problems is to take a small slice, say how far does that slice have to move. The distance for each slice is different. That's why we have to make an integral, because this distance is not constant. I can't say this whole thing moves up 3 meters because some of it's above ground, some of it's not above ground. Each slice moves a different distance. And then we have to add up the contributions of each individual slice, which is adding up an infinite amount of slices, which is why we get an integral. So we need an integral of force times distance. Force is mass times acceleration. Right, that's the whole idea, F equals ma. Right, so mass is density times volume. That's how we're going to build this. And then times distance. Right, so this mass and times acceleration. Density times volume is the mass. Alright. I'll go a little bit more detailed this time, and then the rest of the examples we'll skip some of these details. Remember, the idea is to take a small slice, to thicken it. We're going to thicken it. I'm going to let h be my variable. This is a little bit different than the book does. You're welcome to follow the book's format if you like. I like to think about it in terms of height and distance we're moving. They like to put it on an axis and always use y as the variable. Either way is okay, whatever you are most comfortable with. So we thicken this small little slice, and delta H is the thickness of the small little slice, so that the volume of that small little slice is the area times the thickness. The area of this slice. What is the area of a slice? For a cylinder, it's pretty easy. The area of a slice is just the area of a circle, and the circle has radius 2. The area of a circle is pi r squared, so that's pi times r squared, so that's pi times 2 squared. Right, that's area of the slice, and then multiplied by delta H gets me volume, and then multiplied by the density gets me the mass, right? That's volume times density is the mass, and then multiplied by acceleration. Acceleration due to gravity in the kilograms and meters unit system is 9.8. So this then, mass times acceleration is force. All that's missing is the distance. How far does that small slice move? Okay, so here's where we have to be a little bit careful. I'm going to call this distance h, right? The distance down from the top of the cylinder. Again, there's different ways to do this. Depending on what you label your variable as, this integral will look different, but still be the same, still give us the same result in the end. I tend to like to let h be the distance from the top of the tank. That's not the only way to do it. There are many other ways you could think. We could let h be the distance from the surface. We could let y be the distance up from the bottom of the cylinder, of the tank, whatever the tank looks like. Many different ways to do it. You've got to pick a variable, decide what it is, and then base everything off of that variable. If h is the distance down from top of the tank to the liquid, to the slice. That's what we want. H to be the distance from the top of the tank down to whatever slice we're working with. So what is this distance? This distance is how far the slice moves. So in this case, this slice will move 8 units to get to the top of the tank, plus an extra 3 units to get to the surface. So we're going to have an h plus 3. All right, so 8 units to the top of the surface, h plus 3 units, or 8 units to the top of the tank, h plus 3 units to the top of the surface. Okay, now, that's fine. Just remember that the delta H, the way I wrote this is not quite right. The delta H really is what you would use when you were using a Riemann sum to make an estimate. Then we're taking a limit as delta H goes to 0, as the thickness of my slice goes to 0. That is, the number of my slices goes to infinity. And once we actually take a limit, it really does become an integral, and the delta H becomes dH. So this is really pi times 2 squared times 1500 times 9.8 times h plus 3 dH. And the only question then is, what are the limits of integration? Okay, and this is another part where you have to be careful, especially if we have something below the surface level and we have an extra amount that we're adding to it. Okay, so h is my variable. So this had better be h equals something to h equals something on my limits of integration. So the question is, I want to go from one slice, this is the first slice that goes up to the surface, and then this is the last slice that goes up to the surface. What is the h value at the first slice? Since h is the distance from the top of the tank, that's what we're just defining h to be, the very first h that we're using is 0, because the first slice is 0 units from the top of the tank. So this is h equal to 0. What is the h value at the last slice? The last slice is way down here. H is the distance from the top of the tank, which is the height of the tank. In this case, that's 4. So my final h value is 4. And this is the answer. There's a fair bit of stuff going on here, especially when we have a tank below a surface. But just to emphasize the key points. The key points, to remember force times distance and how it's broken up, density, volume, acceleration, distance. We have to decide what our variable is. I strongly encourage you to draw a picture, write out what your variable is, put it on your picture somehow, and then from there, you just got to remember 2 things. What is the distance that the slice moves in terms of that variable, and what are the limits of integration in terms of that variable? What is the first slice? What is the last slice? And how far do they move in terms of this variable? Okay, let's look at another one. From here on out, I'm going to skip all this, writing all this stuff out, and I'm going to go right to dH instead of delta H. But all of those ideas are the same. Okay, here's another one. Suppose that I have a cone. My tank is going to be a cone. This one's not going to be below the surface, it'll be something else a little bit different. But my tank is a cone shape. right at the surface level. Suppose that the radius of the cone at the top is 2 meters. Suppose that the height of the cone is 3 meters. All right, the wrinkle here is that the liquid is not full. The liquid is only 2 meters high in my tank. Okay, so let's say that the density, that's a delta, lowercase delta for density. Density, let's say that this is water, so this is 1,000 kilograms per meter cubed. What is the work required to pump this water out of the tank? So a couple of things going on here. We'll have to be careful with our what our variable is, just like in the last example. This fact that it's not completely full is going to put a few wrinkles into things. And we also, remember, need to come up with a formula for the area. So the work is this integral of area slice times dH, that makes volume, times 9.8, that's acceleration due to gravity, times the distance. So we have a few things to work on. What is the area slice? What is the distance in terms of some variable? So I'm going to stick with, I should call this big H so we don't have too many little h's walking around. I'm going to stick with my variable as H is still the distance from the tank, top of the tank, to the liquid slice. Right, so all of these liquids, same idea as before. We take some slice of the liquid, and then we need to say what is the work required to get that slice to the top. Okay, so we're going to still call that little h, top of the tank down to the slice. Again, you could choose to do something different. You could choose bottom of the tank up. You could choose top of the liquid down. All of these things are okay. They'll lead to a slightly different looking integral, but that integral is still correct. It would still give you the same and correct answer. Okay, but I tend to just prefer this one, and this is what I'm going to go for the most part. Top of the tank down to whatever my slice is. So what is the area? That's the question. The area of these circles is not constant. In the last example, we had a cylinder, and the area of each slice is the same because it's a cylinder all the way down. Down here, my area is changing and getting smaller and smaller and smaller as we go down. So how do we deal with a cone? Well, we think about it like this. If I slice my cone vertically, right through the middle, it looks like a triangle. This is H. H is the distance from the top of the tank, or the top of the triangle, down to some unknown slice. What I need to know is, what is this right here? Because that's the radius of my slice. That's the this question mark, this half this question, or half of this distance right here. That's the radius of the circle, h units down. So the big distance is 3, and the radius up here is 2. Alright, so far so good. So we need to apply some similar triangle logic. So some similar triangles logic says this. We want the big triangle my big triangle has 2 here and 3 here. My small triangle is this one right here. This green one. So we have to be careful. Right? So the green one, this is the question mark, that blue question mark is what I wanted to know. So this is what we don't know, and let's call that R for radius. Right? So that's the radius of the circle, h units down. What is the height of that green triangle? We have to be careful. Because we chose h to be the distance from the top of the tank down, this distance here is h, which is not the height of that green triangle. The height of that green triangle is actually 3 minus h. So this has got to be 3 minus h. The total of 3 minus the h that we've dropped down. Once we set up our triangles like this, then we can just make a proportion. You can make your proportion however you want, as long as you put the analogous pieces in the analogous positions. Right, so what we've got is 2 over r. 2 and r are the same. Now 2 came from this triangle, so my numerator better also come from this triangle. That's 3, and 3 corresponds to 3 minus h. What's the variable? Well, the variable is h. That's what we're told. That's what we decided at the very beginning. The variable is h. If the variable is h, then that means I better have h be on the right-hand side, and we want r equals. So if we want r equals, then I'm going to bring the r up and bring the 3 down, or we can think about this however we want. This becomes 3r is 2 times 3 minus h, divided by 3, I get 2/3 3 minus h. So r is, based on these similar triangles, we get r is equal to 2/3 3 minus h. So let me save that information. Or we can just point out right away that if that's the radius, then the area slice is pi r squared. So if the area is pi r squared, then this is going to be pi times 2/3 3 minus h squared. That area comes from this radius of the slice that we just discovered. Okay, so far so good. We're going to put the dh at the very end, like a normal integral will look like. We have the 9.8. The final question is, what is the distance? Or what is the distance that the slice moves? Well, because our tank is right at the surface level, we don't have to add 3 like we did at the last time, and because h is the distance from the top of the tank down to the liquid, this slice has to move 8 units to get to the surface. So the distance that it has to move is just h. Right? This slice has to move 8 units. That part is easy. The limits of integration become a little trickier in this case. What is the variable? The variable is h. So what is the variable at the first slice? The first slice is right here. This is where our first slice is. Well, since this liquid was filled 2 meters deep, that means that the first slice actually corresponds to 1 meter below the surface. So the very first h is 1. The very last h is down at the bottom of the tank, which was 3 units down. So the very last h is 3. If we would have chosen a different variable, this would look different, this would look different, and these limits would look different. But they'd give me the same result in the end. But that's the final answer. Okay, let's look at one more. Alright, suppose that we have a swimming pool and it's in the shape of a half circle or a half sphere. So this is a sphere, a hemisphere, a half sphere of radius 5 meters. So the radius up here is 5. Let's say that it's full, and let's say that the density of the liquid is our favorite water, 1,000 kilograms per meter cubed. So we'll have 2 things. We have a different looking shape here, and let's add one other change as well. Suppose that we want to pump liquid out, leaving a final height of 1 meter. So I would like the final height of this tank, of the swimming pool, to be 1 meter, right, in the end, once I'm done. So we start out with the full, we're going to pump it out until there's 1 meter left. Alright, so same basic ideas. We need force times distance, which is area times density, or times dH. That makes volume, times the density, times the distance moved. Volume times density is mass, and don't forget acceleration due to gravity. So mass times acceleration makes force, and finally, times distance gets me the work that is done. So the first trick is always to find the area slice. We want to know what the area of the slice is. So let me do the same thing. We're going to let h be distance from the top, distance down from the top. So as before, we want h to be this. And my question is, and our question is, what is the radius of that circle? It's not a cone, so it's not as simple as setting up similar triangles. We have to do something a little bit different here. But h is but it starts out at 5, it ends at 0, but it has a funny interpolation between. It's not a straight line in between. So it will not be linear. Like the last one was 2/3 times 3 minus h, a linear factor, because on a cone it's coming straight down. This one has a curve to it, a circle to it. So we'll have to do something a little bit different. H is the distance down from the top, and so our question is, what is this radius? We want the radius of that slice, and it will depend on h. So we have to be a little clever here. Let's be a little clever about this in the following way. And once you see this a few times, you start to recognize what's going on. But here's what we're going to do. This distance here is 5. Because this is a sphere, the distance from the center to any point on the sphere is also 5. So this is the key point here. Let me redraw this without so much extra stuff. If this is 5, this is h, this is what we don't know, this is coming in as a circle shape. Right? That's a circle shape, which means that this is also 5. That's the key point. Right? Because this is a sphere, the outside edge is a circle, which means it's 5 units no matter where we go. So I can take that 5 and move it, and it's still 5. So this is 5, this is h, this is a triangle, this is a right triangle, which means I can use the Pythagorean theorem to get r. And this is the r that we want to know. And I can say that h squared plus r squared is 25, is 5 squared. Just as before, h is my variable, so I need to have h on the right as the variable. So if we solve for r, we get the square root of 25 minus h squared. So this radius of the circle, h units down from the top of the tank, is given by square root of 25 minus r squared. Notice that that matches what we want it to be. When h is equal to 0, when I'm at the top of the tank, if h is 0, I get root 25, which is 5, so the radius at the top is 5 as we need. If h is 5, that means we're down at the bottom of the tank. If h is 5, then that's 5 squared, which is 25, which is root 0, which is 0. So down at the bottom of the tank, the radius is 0, just as we need it to be. So that's my radius, which means that my integral will be the area, which is pi r squared, pi times r squared, which is root 25 minus h squared, squared. It's pi r squared, that's the area of the slice. Then multiplied by dh, which we'll put at the very end as before. And that will make volume. So these two things, area times thickening factor, makes volume. Volume times density makes mass. So mass times acceleration makes force. So now we have force. All that's left is the distance. How far does this slice move? Well, as we wrote this out as h is the distance from the top, this slice moves h units. Okay, so if this is h units down from the top, the slice has to move h units. The only trouble then is what are the limits of integration. So we want to know what is h at the very first slice. Well, the very first slice corresponds to the top, which is h equals 0. So the only thing that gives us any trouble is this last fact. We need to leave a height of 1 meter. If I need to leave a height of 1 meter, so in the end, I better have 1 meter right here. Since it's 5 units down, this means I have 4 meters as the distance down from my last slice. So h for the final slice corresponds to 4. And there we have it. So a couple of different things for these types of problems. Always the same strategy. Find the area of a slice. Label your variable. Use that variable the whole way through. Finding the area of the slice is different depending on the shape. If it's a cylinder, it's just a circle. If it's a cone or if it's a pyramid, we need to use similar triangles. If it's a sphere, we need to use this Pythagorean theorem trick. But once we've got the area, it's all the same. Pi r squared, density, 9.8, and then the distance traveled. Now that might be a little tricky depending on the setup of the problem. Most of the time it will just be h, but sometimes if it's below the surface we need to add something else to it. And then finally finding these limits of integration really just comes down to where is the first slice that you're moving and where is the last slice that you're moving in terms of what our variable is. And that's the basic idea for all these problems. See you next time.